Hi guys, myself Dr. Sujatha, Associate Professor from Vignan University. Welcome to the today's session in Design and Analysis of Algorithms. In our previous sessions, we discussed about the introduction of algorithm. From today onwards, we are going to explain about the fundamentals of analysis of algorithms efficiency. Here, this module includes analysis framework, performance analysis, asymptotic notations, recursive and non-recursive algorithms. In today's session, we are going to discuss about analysis framework. The analysis of algorithm efficiency is a fundamental topic in computer science and plays a crucial role in designing and evaluating algorithms. Here, algorithm analysis is the process of evaluating and comparing algorithms in terms of their efficiency and performance. Algorithm analysis is the process of evaluating and comparing algorithms in terms of their efficiency and performance. This analysis helps us understand how different algorithms perform under various conditions and helps us make informed decisions about which algorithm to use for a particular task. To understand and evaluate the efficiency of algorithms, you can use a structured analysis framework that consists of several key components. You can see here the list of those key components. Those key components are input size, running time, space complexity, best, average, and worst case analysis, asymptotic analysis, comparing algorithms, empirical analysis, optimization techniques, and also the practical considerations. Now we will see about each and every component in detail. First and foremost, we are going to discuss about input size n. The size of the input to the algorithm is a critical factor in analyzing its efficiency. In many cases, the efficiency of an algorithm depends on the size of the input data, denoted as n. For example, in sorting algorithms, n would represent the number of elements to be sorted. Right. If size is less, the algorithm, some algorithms may work efficiently. As the size increases, they may not work efficiently. So, the algorithm efficiency or performance analysis must consider the input size. Coming to the running time, which is also to be called as time complexity. This is a measure of how long an algorithm takes to execute as a function of its input size. Here, the goal of this time complexity is to express the running time in terms of a mathematical function. Oftenly, we use big O notation. Not only this big O notation, we have some other notations such as little o notation, omega notation, theta notation. Most probably, we use big O notation, which describes the upper bound of algorithm's execution time. Generally, we represent the time complexities as big O of 1 for constant time, big O of log n for logarithmic time, big O of n, which is to be called as linear time, big O of n log n, which is also a logarithmic time, big O of n square, which is nothing but a quadratic representation for time. Like that, we can represent the time complexity using big O notation. Coming to space complexity, in addition to time complexity, it is essential to analyze the space requirements of an algorithm. The space requirements are nothing but the memory requirements. Space complexity always describes how the memory use of an algorithm scales with the input size n. Like our time complexity, you can use big O notation to express the upper bound of space required as well. And we can analyze in three categories. The time complexity and space complexity can be analyzed in three categories. Those three categories are best case analysis, average case analysis, and worst case analysis. The algorithms can behave differently under different input scenarios. Best case analysis. Coming to best case analysis, it determines the minimum possible running time of an algorithm for a given input size. It represents the most favorable scenario. That is the best case time complexity. That is the minimum time complexity. Average case analysis, it provides an estimate of the running time by considering the expected or average input data distributions. Coming to worst case analysis, this focuses on maximum running time of an algorithm that can take for any input of a given size. This worst case analysis is often the most critical analysis, which guarantees the algorithm's performance in all the cases. So the three cases of analysis are best case, average case, and worst case. We'll see the detailed representation of these three cases while we are discussing about asymptotic notations. Next one, asymptotic analysis. Asymptotic analysis helps us focus on growth rate of an algorithm performance as the size of input n approaches to infinity. So as the size of input increases, how the growth rate of its time complexity is present, or its space complexity is present. That growth rate can be represented by using asymptotic analysis. It allows us to simplify time and space complexity analysis and focus on the dominant terms, ignoring the constant factors and low order terms. And another important component that can be considered under algorithm analysis framework is comparing algorithms. To choose the most efficient algorithm for a particular problem, you can compare the time and space complexities of those algorithms. And generally, we would prefer an algorithm which gives lower time and space complexities for larger input sizes. Coming to the next one, empirical analysis. In addition to the theoretical analysis, empirical analysis involves running algorithms on actual data and measuring their performance. This can help us validate the theoretical analysis and account for real-world factors like hardware and compiler optimizations, etc. Coming to the next one, optimization techniques. Once you have analyzed an algorithm's efficiency, you can explore various optimization techniques to improve its performance. These techniques may involve algorithmic improvements, data structure choices, that is, we can change the data structures, what we are using, and algorithmic specific optimizations. And coming to the last one, practical considerations. In real-world applications, you may need to consider the practical constraints such as implementation details, hardware limitations, and the specific context in which the algorithm will be used. All these components should be considered while we are analyzing the algorithm. These components represents the analysis framework of algorithms. So here, what the different analysis frameworks that we have: input size, how an algorithm performs or works for different sizes of input, running time, space complexity, and different cases of analysis, best case, average case, and worst case, asymptotic analysis, that is order of growth, comparing various algorithms, and empirical analysis, optimization techniques, and practical considerations. I hope that you all understood the key components which are present in algorithmic analysis. Thank you for listening this session. In our next session, we are going to discuss about how to analyze the key factors, time complexity and space complexity for an algorithm. Thank you once again.